Welcome, dear students. Here we are discussing about the physical properties of carboxylic acid. We are dealing with the topic carboxylic acid, of which we had an introductory section where we discussed about the basic classification, nomenclature, structure, such details, as well as preparation of the compound. So that's what we have discussed. Now we go to the next, that is physical properties. And in physical property, we need to specifically deal with the three different property, that is state, the state like solid, liquid, gaseous, the state, then the boiling point, as well as solubility. These are the three physical properties which we need to concentrate with. And in chemical property, first it is about acidic character, and there we need to understand the acidic character of this carboxylic acid or the functional group, uh, especially when there is a substituent present, right? So effect of substituent on the acidic character, that is in one important uh, concept that we need to understand in detail. So that much topic we will cover in this one video. Now please listen. Physical properties, state, boiling point, and solubility. Now when we consider the physical state of carboxylic acids, the aliphatic carboxylic acids, that is carboxylic acids in which there is a no closed structure with double bond or the benzene type ring is not there, they are aliphatic. And in these aliphatic carboxylic acids, which is having number of carbon atoms 9 till 9 up to 9, right? So aliphatic carboxylic acid up to C9, that is 9 carbon atoms in one molecule. They are colorless liquids at room temperature, and they get vaporized, so itself it will spread a smell which is unpleasant, so it is having an unpleasant odor or smell. That's about the state of aliphatic carboxylic acid having carbon atoms still 9, right? So they are colorless liquid at room temperature and has unpleasant odor, right? Now, higher carboxylic acid, that is more than 9 carbon atoms in one molecule. Those carboxylic acids, when we consider, they are wax-like solids. They are not crystalline. They won't become crystalline. They are wax-like solids, right? And since they are solids, they do not vaporize easily and will not spread any smell. So we can say they are odorless. Now why? Because of low volatile nature, right? Volatile nature, being volatile means easily getting vaporized, but these are wax like solids, so they are low volatile, less in volatile nature, low volatility. Because of this property, they are odorless. So that's about the state of the carboxylic acids. Now we go to the next one property, physical property, that is solubility. Here also, first when we consider the aliphatic carboxylic acid having carbon atoms till 4, they are miscible with water. They get dissolved in water. They are miscible with water, right? They are miscible with water, right? And why they are miscible? The reason is the formation of hydrogen bond. So the water molecule is having the HOH molecular structure, and there is in the carboxylic acid also there is hydrogen, so there will be interconnection by making hydrogen bonds, right? So this bond is made and then they mix up easily and they remain in a soluble nature. So itself we can say they are miscible, or they make a very good solution with water, who the carboxylic acid having number of carbon atoms till 4, right? Now when the number of carbon atom increases, the solubility decreases. So we can say solubility will decrease with increase in number of carbon atoms. So when it is C5, it is less soluble. When it is C6, it is still more less soluble. Likewise it will happen. Now what is the reason? Look, all these can come as a give reason type question, so please have a very clear understanding. Now, what is the reason they are less soluble? The reason is that the hydrocarbon part, right? Now, if this is the carboxylic acid unit, and here till total 4 carbon atom, they till that it is soluble. Now if this hydrocarbon part is becoming bigger and bigger, this part is having the nature, what nature? Hydrophobic nature. Hydrophobic, phobia means fear, we know, no? So they are less attracted, or they have less they actually shows a opposition towards the polar nature of the water. They are hydrophobic, not hydrophilic. Philic means attracted, here it is phobic, so it is repelled, or it is not making any type of interaction with the water molecule. So the hydrocarbon part is hydrophobic. So the type of interaction for this hydrocarbon part is what? Hydrophobic interaction. So this one goes bigger and bigger, that hydrophobic nature of the full molecule will increase and the miscibility will decrease, or we can say they are becoming less soluble, right? So that's about the solubility. Now if we just consider the carboxylic acids getting dissolved in other solvents, which solvent? Non-polar. Non-polar means, or usually the organic solvents, right? So the solubility of carboxylic acid in less polar or the organic solvents like benzene, ether, alcohol, chloroform, right? In that also they are appreciably soluble. So that's what carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol and chloroform, right? So not only with the polar solvent like water, polar inorganic solvent like water, in that also they are soluble, and they are the carboxylic acid with less number of carbon atom is more soluble here. When it goes bigger, higher members of the group means they are less soluble, the solubility decreases. So that is the general concept. Again, when we consider the organic solvent, in those organic solvent also the carboxylic acid, they are comparatively good soluble type, right? So that's about the solubility physical property. Now we come to the next physical property, that is boiling point, right? And if you take the other hydrocarbons and the hydrocarbons with this C double bond O unit, or when we compare the boiling point, these are having higher boiling point than the corresponding hydrocarbon. Like if one hydrocarbon having 5 carbon, and the aldehyde, ketone or carboxylic acid also having 5 carbon in one molecule. So if we compare the boiling point of those, the boiling point of this group of compound will be higher than that of the uh, uh, corresponding member of this group. So the comparison, when we do the boiling point of these groups, that is aldehydes, ketones and carboxylic acid, that is higher than that of the corresponding hydrocarbon. Now why it is so? Again, hydrogen bonding is the reason, because of the high extent of, or high possibilities of hydrogen bonding, right? And so itself, when we consider, they exist as associate molecule. Like we can just see what is associate molecule. Just please observe here. This is one carboxylic acid unit, COOH. This is another COOH. Now here you can see there is a possibility of hydrogen bond. And this, look, two units of the same compound, two molecules of same compound, it is attached, and there we can see it is remaining as a dimer. Now the important concept point is that even in vapor form, when they get vaporized, still they can remain as dimer, right? So getting into the vapor form, that is what we say boiling. No, boiling means getting into the vapor form. That happens very slowly because the molecules are tied with each other with hydrogen bonding and they remain as dimer. This hydrogen bond is appreciably stronger, that when they get into vapor form, they sometimes get into the vapor form in dimer form itself, right? So in vapor uh, in the when they get vaporized, they get vaporized as dimers itself, right? So that much strong this hydrogen bond is there. So here we can call it as a associate unit, right? So let's see the theoretical detail. So we can say, because of the presence of hydrogen bonding, they exist as associate molecule. Even in vapor state, the hydrogen bond do not break completely. and most of the carboxylic acid exist as dimer in vapor phase or aprotic solvent, right? Here you may be having a question like the aprotic solvent, what it is. Now if we just quick have an analysis of the term aprotic solvent, it's like those solvents which are capable to furnish H plus ions, they are called aprotic solvent, and which uh, they are called protic solvent, and which are not capable um, yeah, which are not capable to furnish the hydrogen ion, they are called aprotic solvent. Once again, please listen. The solvents which are having the or which have the capability to furnish H plus ion in the solution, they are called protic solvent, and which do not have the capability to furnish H plus ion, they are called aprotic solvent. Here a definition is not much relevant relate about aprotic solvent, but in the um, physical chemistry, if you are dealing with the solubility as well as the acidic and ionic equilibrium and all those details, there it may be come useful. Just related to that concept, if needed, have a clear understanding. Here it just for the term knowledge, you can understand that aprotic solvent means the solvent which is not capable to furnish H plus ion in the solution. So that's about the boiling point. Here we said when we consider the boiling point, the pure carboxylic acid getting vaporized at the boiling temperature, that happens slowly by absorbing more heat energy. That's why we say boiling point is higher. Boiling point is higher means it needs more energy to get vaporized. The reason is that the molecules are attached together in a dimer form or in an associate molecule form because of the presence of hydrogen bond, right? So here you can see these are carboxylic acid units itself remaining as a dimer, and in the vapor form, when they get into vapor form, likewise itself they get into vapor form. Here they are remaining in a solution, and even in a concentrated solution form, they here you can see this is a water unit. This is a H2O water unit. This is one carboxylic acid. This is another carboxylic acid unit, and this is another carboxylic acid unit. You can see it is remaining as a big associate molecule, right? So it will remain like that in the solvent as well as in vapor form. So itself the boiling point for the liquid to reach the boiling temperature, it needs more heat energy, so we say the boiling point is higher. So that's about the three different physical properties recommended for our learning related to carboxylic acid. Now we come to the chemical property, and in chemical property, first we are dealing with acidic character, right? Then the formation of and the other chemical property which we need to discuss, we'll just have a quick look. Acid chloride formation, decarboxylation, then substitution of the benzene ring, as well as finally we need to have a understanding related to how to distinguish formic acetic and benzoic acid. So test for formic acetic and benzoic acid, these are the chemical properties which we need to go through, of which this acidic character we are discussing here. Now if you consider the carboxylic acid, when they react with the metals, they are behaving like, we are just discussing about common reactions of acids. Even in inorganic chemistry, we know when acids are treated with metals, it liberate hydrogen. So here we are just going through certain reactions which help us to understand that the carboxylic acid involved in chemical reaction as if like an acid, and thus we are just going with a primary explanation for the acidic nature of carboxylic acid. So first of all, carboxylic acid, when they react with metals, they evolve hydrogen. Now if they react with alkalis, they form salt, right? Now when they react with a carbonate or bicarbonate salt, they evolve carbon dioxide. So these all are reactions done by acids. So here carboxylic acid shows these reactions, so we can say they are showing the acidic nature, or those are proof for the acidic nature of the carboxylic acid. Once again, carboxylic acid evolves hydrogen with metals, form salts with alkalis, as well as evolve carbon dioxide with weak bases like the carbonate or bicarbonate salt, right? Now these two reactions, like this reaction, it is same like for alcohol, this is again same like for phenols, but this reaction, it is opposite to that of phenols. These are certain concept which is shared for us to make a comparison, so that we can feel like memory is little supported. So here this reaction is same like that of alcohol, this is same like of phenols, and here this is actually different, opposite to that of the reaction involving phenol. Now we will just go with some examples. Look, this is carboxylic acid reacting with a metal, especially the active metal. So itself it is given in our syllabus. So with active metals, you can see it liberates hydrogen, right? So that's about the first reaction. The carboxylic acid reacts with the active metal, one of the most active metal, sodium, and you can see the salt of the acid is produced, sodium salt. When it is sodium metal, it is sodium salt of acid produced. Along with that, hydrogen is liberated, right? Continuing with alkali, you can see NaOH, it is a strong alkali. Here the carboxylic acid reacting with an alkali, producing the sodium salt of the corresponding carboxylic acid and water. So you can see with an alkali it is giving salt and water, right? So that's also indicating the acidic nature of carboxylic acid. Now here you can see this is carboxylic acid reacting with a carbonate salt, right? And here you can see carbon dioxide and water, same like how an inorganic acid react with a carbonate salt, evolving carbon dioxide and water, these two as the byproduct, and the salt of the corresponding salt of the acid is produced. So that's about how it reacts with carbonates. Now with bicarbonates, when we consider, again you can see the acid reacting with bicarbonate salt, giving the corresponding salt of acid, along with that water, a byproduct, and carbon dioxide is also evolved. So with carbonates and bicarbonate, it liberates carbon dioxide and water is formed as a byproduct. Along with that, the corresponding salt of carboxylic acid is produced. So that's about the basic reactions showing the acidic nature of carboxylic acid. Now we are just going with certain theoretical details of carboxylic acid, how it functions as an acid. Now we know acid, when added with water, it ionizes and liberates H plus ion. That's why we call them as acids. In the case of carboxylic acid, in water, this carboxylic acid functional group, it will ionize, right? And the ionized unit exists in a dynamic equilibrium condition. We can see this is the carboxylic acid unit, this is water molecule, H plus ion is liberated and the hydronium ion is formed, and here you can see this is the carboxylate ion. Here you can see the double bond getting shifted from this position to this position. So this is you can see the two structures, right? And here uh, this because of the presence of this resonance formation, like this is canonical form, this is another canonical form, together existing as a resonance hybrid, right? So this is stable, and hence this is also can remain active in the solution. So you can see this is the resonance hybrid, right? This negative charge can shift through this path. So that's about it. Now here if you just go with that equilibrium constant, just for us to compare the acidic nature, we will just have a, this is not how much detail is needed, however it is, we are just going to the deep so that we can have a clear understanding. So any level question we will be able to answer here. As you have learned in the ionic equilibrium, this is how the equilibrium constant, the concentration of the products, concentration term of one product, this is another product, right? And then here you can see the reactant, this is the other reactant. This ratio gives the equilibrium constant, and the concentration of water is taken as a constant, so it is shifted towards the other side of the equation, and then we get Ka. This term is taken as Ka. Ka is equal to concentration of hydronium ion into concentration term of carboxylate ion divided by the carboxylic acid unit, right? Now we call it as acid dissociation constant, right? So this is just for the theoretical understanding. if you get some question related to the possibility or the stability of carboxylate ion or the reactivity, acidic nature, they're all, or if you have the deep understanding, it will be easy for you to construct the reason. So just for that purpose, have a clear understanding. So that's about the acid dissociation constant. Now please listen, dear students. You can see the strength of the acid. It is indicated by pKa value, if you remember. Now how can we get pKa value? If you take the negative logarithm of Ka can be calculated by knowing the concentration of the ions present in the solution as well as the substrate molecules which were taken. With that we can find Ka value, and if you take negative logarithm of that, we will get pKa. Now with respect to pKa value, we are defining the strength of the acid, right? If the pKa value is smaller, the acid will be strong. Now if you just go with the general concept, pKa value less than 1 means it is very strong acid. For example, trifluoroacetic acid. You can see trifluoroacetic acid. Right? All the hydrogen removed and fluorine, the most electronegative fluorine is taking the place. So that is trifluoroacetic acid. It is the strongest organic acid, and you can see the value 0.23. Remember one thing very properly, organic acids are comparatively less acidic than the inorganic. Inorganic acids are highly strong, right? Now organic, when we compare the organic acids with inorganic acid, the strength, the acidic nature is comparatively less. Now generally when we take organic acid as a single group, the strongest among them is trifluoroacetic acid, and for that the pKa value is 0.23. and if you just go with the pKa value of inorganic acid HCl, it is negative 7.0, and benzoic acid it is 4.19, acetic acid it is 4.76. Likewise it is, just for comparison. Now just please look, if pKa value is below 5, that is between 1 and 5, we can say it is moderately strong. So below 1 means it is very strong. 1 to 5 it is moderately strong. Now if 5 to 15, if pKa value is between 5 and 15, it is weak acid. And if it is above 15, greater than 15, it is extremely weak acid. So here we are taking pKa value and we are explaining just the acidic character of the compound. If the value of if pKa value is less than 1, it is strong acid, very strong acid. Between 1 and 5, it is moderately strong. Between 5 and 15, it is weak acid. As an acid, it is very weak. Now, if it is above 15 means it is extremely weak acid, right? So that's about just a comparison of the acidic nature with respect to pKa value. And the strongest organic acid, which is trifluoroacetic acid, it is having pKa value 0.23. 0.23. So that's about certain details. Now we'll just go with the resonance stabilization of carboxylate ion and understand the acidic nature. Please be attentive, okay? Just feel free, relaxed, and believe that it is easy for you to understand. Then it will be, you can understand it very easily. You can see this C double bond O COH. This is the carboxylic acid functional group. This double bond can be shifted to here because of the electronegative nature of oxygen, and then this carbon will have a positive a partial positive charge, which will enable carbon to absorb this lone pair of electron, and the double bond will be formed here, right? A double bond will be formed here. Just so there was a small correction in this board work written. Look, this you can see this double bond is shifting here and it is gaining a negative charge, and here there is only single bond now. In the written, if you see it as a double bond, it's a mistake. There will be only a single bond now because the double bond electron is shifted to this position. Now what? Here this lone pair electron attracted here, and it is a double bond is created here. Now what will be happening? Comparing the proper nature of oxygen, the electrons are shifted to this position. So this oxygen is gaining a positive charge. This oxygen is gaining a positive charge, right? Since it is gaining a positive charge, it will attract these electrons here, and there is a great tendency for this H to get removed as H plus. So this H plus is what we call as a proton. So proton is removed, right? Now here, this is the first formation. This is here, this we can call as the carboxylate anion. This we can call as carboxylate anion, because this is, because of this positive, this is taken, right? Then this positive charge is satisfied there, and this is released as positive ion. Then the charge here is only negative, so we call it as carboxylate anion. You can see here, look, that these two electron, it is taken, the electrons which was shared here was taken by this oxygen, and thus the lone pair of electron is reformed here. So this is after release of the proton, this is the structure. And here again you can see this electron can get shifted to this position, right? This electron can get shifted to this position, and this can be shifted back to this position. So look, again there will be a shifting of the double bond from one position to the other position. What is the net effect? The net effect is that the negative charge will be shifting in this between these atoms. This negative charge will be shifted. You can see, like we can just put it like this. This negative charge will be shifted in this part between these atoms of this radical, right? That is the net effect, right? So here, even this carboxylate ion is having resonance formation, possibilities of resonance, that is different structures are possible, and that itself create a stabilization in this carboxylate ion, so they remain as a stable unit, and that actually makes H plus to remain in the solution and show the acidic character, right? So that's about the acidic nature of carboxylate ion. Now this is a next point that we need to consider, effect of substituent on acidity. Okay, this is the carboxylate unit, and there is a substituent here. Now the presence of substituent, how it affects the acidity of this carboxylate unit. That's what the next one concept that we need to understand. You can see the substituent may affect the stability of the conjugate base, this also affect the acidity. Okay, I hope you remember the concept of conjugate base, which you have learned in your ionic equilibrium topic in your 11th standard. Maybe you had some continuation in your 12th standard in your physical chemistry. Like if you just consider two water molecule here, one water molecule is acting as an acid, this is acting as a base, right? Now this is ready to accept 1H plus, this is ready to accept 1H plus, and it is forming hydronium ion, and this is ready to release 1H plus and make OH minus. So likewise, this remain as one pair, and these two remain as another pair. These two remain as one pair, and these two remain as another pair. So we can say these two are the conjugate acid base pair, and these two are the other conjugate acid base pair. So that's the concept of conjugate acid and base, right? So here, when we consider this presence of a substituent, that actually affects the stability of the base pair of the corresponding acid, right? The base pair of the corresponding acid. That's why we say that will affect the acidity. So we will just go with the explanation here. Please listen. Now this carboxylic acid unit is attached to a substituent. The substituent is what? Electron withdrawing group. It absorbs the electron. So this will gain a delta negative charge, and here it will be a delta positive charge, right? When it is having delta positive charge, the electron will have an attraction towards this, right? Electron will have an attraction towards this. So itself, the oxygen will attract the electrons here and will easily release the H plus ion. So we say they are highly acidic, right? So we say they are highly acidic. So here what we can say, the electro withdrawing group is creating a partial negative charge here, and partial positive charge here, that makes a attraction of the electron to this side more effectively, and the hydrogen ion will be released easily. So we say acidic nature increases. Now this formation of this partial negative charge, we call it as negative inductive effect. So what we can conclude, if an electron withdrawing group is remaining as a substituent, there will be negative inductive effect, and increase in negative inductive effect increases the acidic nature. So that is the final conclusion, right? So you can see the presence of the electron withdrawing group actually increase the stability of carboxylate ion, increases the stability here, and that will actually cause the H plus to be released faster. So that's increasing the acidic nature, right? So that's about the one condition, and this is about the opposite condition. When it is electron donating group, the electrons are shifted to that side, right? The electrons are shifted to that side. So what? Then this oxygen will actually get decreased with its electronegativity. The electronegativity of oxygen will get decreased, right? And so itself, there will not be much attraction on this electrons here. There will not be much attraction of the electrons here, and there is less chance for hydrogen to get released as H plus ion. You please hear the explanation repeatedly. The electrode donating group donates the electron, or the electron shifted toward this side, and this oxygen also satisfied with electron. So there is no less chance for the electron pair to get attracted here, and less chance for hydrogen to get released as H plus ion. So what we can say, electron donating group means what? Positive inductive effect. You can see partial positive charge created here. So positive inductive effect, that will actually decrease the acidity. That will actually decrease the acidity. So it's very important. You can just go with the positive and negative inductive effect, get a deeper idea about it, and relate to this situation. Just basically what we can say, negative inductive effect due to electron withdrawing group increases the acidic nature of carboxylate unit, and positive inductive effect due to electron donating group actually decreases the acidic character of carboxylate unit. So that's about the present effect of substituent on acidity of carboxylic acid. And here all some comparisons are given. You please relate it with the positive and negative inductive effect and have a deeper idea about it. uh, uh, you can get question like give reason, or you can be given some examples in this bracket, and you will be asked which is having which carboxylate molecule will be having higher acidity, lower acidity. So there all you should just have a basic idea about the increase and decrease of the positive and negative inductive effect, and then theoretically itself you can relate and find to the answer. So that's about the effect of substituent on acidity. Since we are also given with the present the aromatic carboxylic acid, we will have a quick look into this concept also. If a phenyl unit is attached, actually the acidity will be increasing, right? Even the phenyl unit, that is a benzene ring, is having a resonance stabilization, and we expect the possibility, the expect it to be less acidic, but it is having greater acidity. And the reason is due to a shift of the hybridization of the carboxylate carbon. You can see the carbon, when we consider, okay, the carbon which is attached to the this carboxyl carbon atom. This carbon atom will be shifting from one hybridization to another hybridization, and sp3 hybrid, then less electronegative and less acidic, right? If it is sp2, it is more electronegative and more acidic, right? And sp means it is most electronegative and it will be most acidic. So the electron will be attracted. Electronegative means it will attract the electron, so the greater tendency to release hydrogen. That's how you should relate. Less electronegative means less attraction to electrons and less possibility for H to get released as H plus ion. More electronegative means this part will be having greater attraction absorption of the electron and greater possibility for hydrogen to be released as H plus ion, right? So and when the hybridization from sp3 to sp, when we consider this carbon, if it is sp3 hybrid, means it is less electronegative, so itself less acidic. Likewise, that comparison also please have a basic understanding. And here also you are given with it C bonded, this carbon involved, not attached to any other carbon, means sp3 hybrid, right? Here this carbon is attached to another one carbon, and that also with a double bond, so what, here the type of hybridization from sp3, it has gone to sp2. So this is more electronegative and more acidic. This is less acidic. This is comparatively more acidic. Here again, it is also more acidic. Now, when we compare these two, this is also sp2, this is also sp2. Still, this is more acidic because of the delocalization of the double bond. Possibility of delocalization of the double bond inside the benzene ring, right? Now again, when we come here, this carbon is attached to this carbon with a triple bond. So this carbon is undergoing what type of hybridization? Sp hybridization. So this carbon is much more electronegative, and so itself the electrons will be shifted towards this direction, and H will be released as H plus ion. Greater possibility. So more acidic, right? So that's about the acidic, all the different angles we are considering the acidic nature of the COOH unit. So please have a clear understanding. You hear it once, twice or thrice. If you have any doubt, you can personally just contact so that we can clarify it. Now here, likewise, actually this, just have a quick look into this. When we consider this benzene ring still having another substituent coming, right? Another substituent when it is coming, when they are electronegative substituent when it is coming, you can see the this is having greater acidity, and likewise the acidity decreases. And when it is electro then likewise when we consider, you can just keep this order in your mind. Some objective type, actually substituent to the benzene ring is not asked, but still have a quick look here. When we consider the substituent on benzene ring when it is coming, how the acidity is changing. The acidity here, it is greater acidic, and the acidity decreases in this order, right? So that's about the acidic strength of the aromatic acids in which the benzene ring is still having another substituent atom or group of atom present. So that's the comparison and learning related to the acidic nature of carboxylic acid. So here we were just going with this one property, and now we had a comparison of the acidic nature of aliphatic and the aromatic carboxylic acid, how and why it is happening like that. So please have a clear understanding. The rest of the chemical reaction we will include in the next video. Thank you.